On the other hand, if we want to solve logarithmic equations, we kind of play the same game, just in reverse, for the fact that these things are one-to-one functions and their inverses are defined as exponentials. So, if we have a nice logarithmic equation, something that can be written in form the logarithm is equal to a constant, then what we're going to do is start by expressing the equation in that form, log base b of m is equal to c, then use the definition of the logarithm as the inverse to write it in terms of an exponential instead, solve that exponential, and check that the solutions to the exponential are valid for the logarithm we started with. Where that last step is actually very important, because you remember when we're talking about the domain of an exponential, that can be anything, but the domain of a logarithm must be positive. So there are cases where we're going to end up with values, it's going to happen fairly often, that the solutions we have aren't all valid, or sometimes none of them are valid. So we do need to check to make sure that things work the way we expect them to. Let's get a couple examples to see how the process runs. For this, we want to solve the equations log base 2 of x minus 4 equals 3, 3 natural log of 4x equals 9, and log x plus log x minus 21 is equal to 2. And again, here we're in that form we like, so a lot of this is just going to come down to maybe some condensation of logarithms and pulling around with exponents. So for our first one, we are in a very natural form to deal with this sort of thing from the start. Log base 2 of x minus 2, or excuse me, x minus 4. Yep, I did get that right, I just misspoke. Where this is equal to 3. And with this set of information, there aren't really any expansions or things we could pull together in a particularly logical way, even if we wanted to. Like, suppose we could divide out a 3 and then bring a cube root into there, but I don't think that would actually help us at all. Instead, really what we have is a situation where we want to use the fact that this is the inverse of something with a 2 raised to a power and then rearrange. That is, we take this relationship here and recognize that up to rearrangement, it's the same as saying 2 cubed is equal to x minus 4. And this is a very simple, relatively simple anyway, linear equation to solve, as we cube that 2, get 8, add 4 over, and we will end up getting x equals 12. Where if we want to be sure that x equals 12 is a valid solution here, we can plug that in. Log base 2, 12 minus 4 equals going to be log base 2 of 8, where that is asking the question, what power of 2 is 8? 2 cubed is 8, so this is equal to 3, and that's a valid solution. Which means if you want to write the solution set for this, we would get something like, excusing my funky notation here, the set of the number 12 and nothing else. Then for our second example, we're going to do basically the same thing. Here, if we really wanted to, we could pull in that 3 because it's already there, put it in as a cubed, make that 64x cubed equals our answer. Maybe that'd make our life easier, maybe it wouldn't. Me personally, I see that work there with the 9 on the other side, and think to myself, it's easier to deal with division of constants than it is to deal with cube roots. So I'm going to deal with division of constants. But it works the same way. And then also, if you really wanted to, you can maybe split this thing up a little bit like we have in other sections, but we want that condensed as much as possible because when it's all stuck together into one term like this, we can just immediately apply the work like we did up here with changing out to an exponential. Anyway, from here, this is the same as saying that the natural logarithm of 4x equals 3, or, if you prefer, and I generally would, e cubed is equal to 4x, so x is equal to e cubed over 4, where this is the best way to write that answer. If you multiply that all out, you'd get something between 7 and 8, I believe. I don't have an approximation here on my sheet in front of me. You can check that for yourself if you really want to. But this is the most precise way to write that answer. I would prefer it be left in that form, where if you want to be sure that this actually works, that this is a correct answer, we can plug that back in up here. I'm not going to write that out just because I'm a little short on space, but you should see that if you plug that in, the 4's would cancel. You would get the natural log of e cubed. The natural log of e cubed, by definition, would be 3, because it's looking for powers of e. 3 times 3 is 9, so we're good. That tells us our solution set, if we wanted to write it in terms of set notation, is e cubed over 4, just like you saw there. So with our third case, we're going to play the same sort of game, except at that first step, we're going to recognize that the common logarithm of x plus the common logarithm of x minus 21 can be rewritten in terms of a multiplication as the common logarithm of x squared minus 21x. And that allows us to put things back in terms of powers of 10 here, because this, as we started, is equal to 2. So you could equivalently write this as, if you prefer, and for our purposes we do, 10 squared is equal to x squared minus 21x. Sorry, gears are turning a little bit slower at the moment. We'll get sped up as we're going. Then we can pull our terms around here and leave ourselves with the quadratic equation 0 equals x squared minus 21x plus 100, which hopefully you can see is factorable and factors into two terms that x would either have to be, in this case, -4 or 25. And if you want to check those, you would plug both of these into our original equation, where if you plug in 25, you'd get log base 10 of 25. Here you'd get log base 10 of 25 minus 21, so you get 4. Or if you want to put them just into here instead, even a little bit quicker, either works. But the point is, you stick those two together, you get the 25 times the 4 using the product rule. You'd get 100, which is 2 in terms of the logarithm base 10. Meanwhile, if you plugged in -4, it might seem like you could play the same sort of game, pulling them together, because it'd kind of cancel out the negatives. The problem is, it would involve starting with putting in a -4 there to begin with. And that's not a valid place to begin from. No matter where you end up, you can't just throw that in there and hope for the best. So actually, that -4 would be invalid. And if you want to write our solution set, it would then just consist of the number 25. And that's how we handled our nice case for dealing with logarithmic equations. The next thing we're going to look at is our slightly more complicated case, where we have more logs on both sides to manage. But it still works under very similar logic in terms of being able to bring in exponentials to remove the logarithm.